Okay, so yesterday we stopped after some examples of manifolds. So we recalled the definition of manifold, and we just recalled a few examples. In particular, I think the most important one was the projective space. Then we also talked about the Grassmannian. Today we will continue with our review, and we will start with another definition you should be familiar with, and that is the one of orientability. So we have a smooth manifold M, and we say that it is orientable if there exists an atlas U, J, phi j, such that the determinants of the derivatives, so derivatives here means the Jacobian matrix, are positive for all j and k. Okay, and so this is yeah, the determinant of the Jacobian matrix. For all j and k, of course, such that uj intersected uk is non-empty. Otherwise, it doesn't make sense. And yeah, so this kind of means that when you're gluing these local charts, you're gluing them on the same side somewhat. And the proposition here concerns complex manifolds. So if we take M a complex manifold of complex dimension n, complex dimension n, then of course M is also a smooth manifold of real dimension to n, and it is orientable. Yeah, so if you have a real manifold, so a smooth manifold M, you can, sorry, not real, but complex manifold M, you can always see this real manifold of double the dimension. And as such, it is an orientable manifold. And this comes from the Cauchy-Riemann equations. So let's just give the quick proof of this fact. So we take complex, yeah, so this is a complex atlas of M, and we take alpha beta such that u alpha intersected u beta is non-zero, and define F to be phi alpha composed phi beta inverse. So this is a map between open subset of C, and as such we can write it as the real part plus the imaginary part. And here U and V, they're from some open subset in Cn to Rn each. Yeah. But we don't want to think them as functions from Cn, but from a subset of R to n. So write U of x1 plus I y1, etc., xn plus I yn. So if I think about it this way, I think of U as a function of n complex variables, but I want to think it as a function of 2n real variables. So I'm going to write it like this instead. And the same for V. Okay. So now I can really think of f as a function from R2n to R2n, basically. This is by identifying C with R2. And now we have what my claim here is that if you look at this map F, which is nothing but phi alpha composed of phi beta, and then if you want to be formal, pre-composing and post-composing with the identification of Cn with R2n, what we want to show is that the determinant of f is positive everywhere. Okay, so let's compute that. So this matrix, well, here in the top left corner, we will have the derivative of u with respect to x. And when I write this, of course, x is an n tuple. So you're a mean n times n matrix. Yeah. So this, I'm writing this in block notation. And here also we have the derivative of u, but with respect to y. Here we have the derivative of v with respect to x, and here we have the derivative of v with respect to y. And this point is very simple to use the Cauchy-Riemann equations. So this is CR equations, which tell us a relationship between the derivative of the imaginary part and the derivative of the real part of a function. So here we have negative du in dy, negative du in dx. So this is thanks to the Cauchy-Riemann equations. And yeah, now if we look at the determinant of this, this is nothing but du in dx. Oh, sorry, determinant of du in dx square plus determinant of du in dy squared. And this is therefore always positive, as these are two real numbers, and they're never simultaneously zero. Of course, we have to say that because u was itself the real part of a bialomorphism, so these derivatives cannot be zero simultaneously. Okay, so to recap what we did so far from the newcomer, we have they've just defined what is an orientable manifold and proved that a complex manifold, if seen as a 2n-dimensional real manifold, is also orientable. Now we'll recall another important property of manifolds, of smooth manifolds. This is really a property of smooth manifolds. So definition, smooth manifold, and then we take a cursive view, a locally finite covering, and we say that the family phi alpha with phi alpha from mu alpha into R smooth is a partition of unity associated to the covering, associated to u, if number one, all these are positive or non-negative, to be precise. The support of phi alpha, which by definition is nothing but the set of x in u alpha, such that phi alpha of x is non-zero, and then you take the closure of this, is compactly contained in u alpha. So this double contained means compact inside. Yeah? So the support doesn't touch the boundary of this u alpha. And the third property, and this is the key property, is that the sum of phi alpha x, so the sum is over alpha, is identically 1 for every x in M. And maybe observe that since the covering is locally finite, locally finite covering, this is actually a finite sum for every fixed x. So we don't have problems of convergence. And if you're scared that phi alpha of x is only defined inside of u alpha, so what happens if x is not in u alpha, you just define it to be 0 there. Okay, and this still gives a smooth function because the support is compactly contained in u alpha. And now we have a theorem. Theorem is given a manifold Whenever I say manifold, I would always mean a smooth manifold unless otherwise specified. Again, locally finite. Covering such that each nu alpha is relatively compact in M. So relatively compact means that this closure is compact. Then there exists a partition of unity associated to M, to U. Okay, so basically every time you have this nice covering by a locally finite covering by relatively compact sets, you always get a partition of unity. And we will not prove this because the proof is rather hard and long, and you should have seen it already in previous courses. Just a couple more definitions.
I have a question about that. Here in the theorem, we only require M to be a manifold, but that has to be smooth, right?
Yeah, exactly. I mean, maybe can you repeat the question?
My question was only if it has to be smooth or if CK or C0 is enough.
Okay, so in the course we will kind of never deal with CK manifold. We'll always deal with either smooth manifold or holomorphic manifolds, or complex manifolds. I am not sure if partition of unity worked for C0 manifolds. I'm pretty sure it worked for CK manifolds because it's mostly topological. It's mostly a topological proof. I would be a bit wary about topological manifolds, that is C0 manifolds. But I believe, but I wouldn't bet on it, that if I have M a CK manifold with such a locally finite covering, then there exists a CK partition of unity for that covering. So of course you cannot talk about smooth functions in a CK manifold. You can talk at most about CK functions. So this partition of unity cannot be smooth, it needs to be CK. Did I answer your question?
Yes, thank you.
Okay. Okay, let me define a manifold with boundary. Boundary. If the local charts, is there a question? Map into open subsets of Hn, and this Hn is nothing but this half space. So x in Rn such that x is n is greater or equal than 0 instead of Rn. So what does it mean? Okay, I made it very short. So you look back at the definition of manifold. So M is basically the same as a manifold, but normally the local charts map into open subset over N. Instead of taking that, you take open subsets of this half space, closed half space. Yeah. And define the boundary. M is boundary M, written like this. And this is just the union alpha of the anti-image of the boundary of Hn. Yeah, so for each local chart here, you have a clear boundary, which is just xn equals 0. And you take these hyperplanes and you send them back and you call this the boundary of the manifold. Okay, you have to be careful here because you don't know if like the boundary is sent to the boundary, but this is something you can check, and I believe you already seen this definition, so we will not do all this checking. I just wanted to recall it. But if you do not remember it, or if you've never seen it, you can prove that this is in fact a manifold of dimension 1 less than, so dimension n minus 1. And also, if M is orientable, so is boundary M. Okay, and M orientable for a manifold with boundary actually means that the interior of M, so M minus its boundary, which is a manifold, is orientable. Okay, so this concludes our recall about manifolds per se. And now I would like to recall another few facts about constructions that we can do with manifolds, in particular with their functions. And so we will now talk about structure sheaves, structure sheaf, tangent bundle, and differentials. Okay. So again, I expect that you've seen all of this, but this will be very important for the future. So I would like to recall it. In particular, I think you know that the tangent bundle has many different definitions. You have the one where you have like equivalence classes of small segments. Then you have the one with derivations. So there are a few ways to define it. And there is one in particular which would be important for us, which is the one where you define the tangent bundle as derivations, which perhaps was not given too much attention to in the past. So that's also why I want to recall it in this way. So really define it as the set of derivation. But we will get to that in some 15 minutes. So we take smooth or complex manifold. And we fix a point. We consider GP to be the set of all such pairs UF, where U is an open neighborhood NGH of P, and F is a smooth function on U, or in the case of a complex manifold, a holomorphic function on U. Okay. So this is the set of all functions which are smooth or holomorphic in a neighborhood of P. And now we define an equivalence relation. Define an equivalence relation on GP by saying that the pair UF is equivalent to the pair VG if and only if there exists some other open neighborhood of P, open neighborhood of P containing U intersected V, such that if you restrict F and V and G to this W, you get the same function. Okay. And we define the equivalence classes, I mean the set of equivalence classes, to be the so-called space of the germs at P. Space of germs of functions at P. And we denote it by, well, either C infinity MP or holomorphic MP. Okay. And the equivalence class of one particular function or one particular pair, valence class of UF is FP. Okay. So exercise / recall. So again, exercise if you don't feel comfortable with these objects. And the thing is that the spaces of germs are actually rings or commutative rings. And when I say rings, some authors distinguish like a ring might not have a neutral element for multiplication, while some authors define a ring to already have a neutral element. So for me, rings always have a neutral element for multiplication. So with neutral element, but I will not repeat this. And in particular, the latter is an integral domain. While the other is not. Unless m is a point. So integral domain, if you don't remember, means that there is no zero divisors. So if A times B is 0, then either A or B must be 0. I mean, or both, but at least one of them must be 0. And let's also observe that the map, which sends a germ to its base point, so MP R, it takes FP and sends it to F of P, is well defined. Yeah, because of course this is an equivalence class, but if you take something which is equivalent to it, it must be the same in the neighborhood of P. So in particular, the same at P. And so everything is good, is well defined and surjective. Of course, you can just take all possible constant functions and they give you different values here. And this is also a morphism of rings. Well defined, surjective, and ring morphism. Of course, if you take the multiplication of two functions, then the evaluation of a point is just the product of the two evaluations. And same with sum and with multiplication by R. So this in particular, so since R is a field, since R is a field, this also proves that MP, which is the ideal of FP in C infinity MP, such that F of P is 0, is a maximal ideal. Because again, maybe you remember from algebra that if you take a ring and then you take a quotient of this ring, in this case we have a ring modulus the kernel equal the image. If this image is a field, then the kernel that you've been dividing with is actually a maximal ideal. It's an if and only if. Okay. So now let's try to make this construction a bit more general, let's say, not exactly. But now, see, what we've done now is taking a point, and consider all possible functions near that point. But what if instead of taking a point, we take a full open set? So we take an open set, and we define it's infinity U, and the same ways for holomorphic. Yeah? when we have a complex manifold, the set of all functions from U to N such that F is smooth. So you're basically associating to an open set U just the set of all functions, of all smooth functions defined on U. And of course, this should not be M, but should be R. And this is C, and this is replaced with holomorphic whenever our manifold is complex. So and so this is called the structure sheaf. So not like the operator. So you can think of this as a what is called the functional. I don't know how much you know about category theory, but just for us, it's just a function, let's say, that takes open sets of M and returns sets of functions. Actually, not just sets of functions, but rings of functions, to be more precise, is called the structure sheaf of M. Okay. So here we see the word sheaf for the first time. This will become a very important part of the course later on. And yeah, it's this idea that you take a manifold and to every open set, you associate something. And in this case, this something we're associating is just this rings of functions. In the future, we will often associate rings. And as we said before, we can see functions sections of a particular fibration. So this is something we will also do. But again, this will come in quite a few months. Quick exercise, again, that I believe you can do in your head. So if M is a complex manifold, complex compact manifold, then it's a structure sheaf. If you evaluate it on the open set M, so everything, it is just the LOC. And this is equivalent to say that all holomorphic functions are constant. Yeah, so if you have C here, it basically means that for every constant, you have a function, and the function is the constant function. Okay. So maybe this is also a nice way to review some theorems in complex analysis. So now let's go with the derivations, vector fields, and tangent space. So what is a derivation? V on the set of germs is an operator from the set of germs to R and to C in the case of complex, such that a few properties are satisfied. So we want linearity, so it's a linear operator. And here's for every lambda in R and FP in infinity MP. And again, just remember that you can always replace R and this smooth structure sheaf with the holomorphic structure sheaf and C. So we have, this is just linearity, yeah, and then we have the so-called Leibniz rule, which is really what gives us through derivation. So this is a ring, so we can multiply them, and what you get here is the evaluation of f at p times the derivation of g plus the evaluation of g at p times the derivation of f. Okay, and we say that the set of all derivations of C infinity MP is denoted by TPM. Okay, and called the tangent space, of course. At P. Okay, so we say that, so this is kind of a very algebraic notion, but we will see really in practice what this means. And of course, we can see that this is a vector space. If you have two derivations, you can easily sum them and multiply them by a scalar. And now we want to describe this set of derivations a bit better. So in some sense, the set of derivations is a subset of the dual of the structure sheaf, yeah? Because all linear functional of the structure sheaf would be basically the dual of the structure sheaf. Here we ask this extra condition, which is this Leibniz rule. But there definitely should be some relation with this. So we want, the first thing we want to do is study the structure sheaf a bit better. And the first thing we will do is show that we can reduce ourselves to the case where M is just Rn. So let's take U phi to be a local chart. And observe that the map phi star, which we will now define, which goes from infinity Rn phi of p to infinity mp, defined as phi star of f p equal f compose phi at phi of p. At phi of p? I think so. No, sorry, my bad. My apologies. The points are all wrong. So this should be an element here. So this is f at phi of p. And this is f compose phi at p. Okay, so we define it this way. We just pre-compose with phi, and we keep track of the point we're currently about. We have that this map is a ring morphism, isomorphism. Yeah, so it's not just morphism, it's actually a ring isomorphism. And you can see this because, well, phi is it's itself a diffeomorphism. So we can go back and forth. The inverse of phi star would be phi inverse star going in the other direction. And also, we can consider the differential of phi. And now this is a map from TPM to T phi p over n. And okay, in principle, this map, we don't know what it is, right? In the sense that, okay, you know that the differential of smooth maps exist. But for now, this is just a symbol, which we define as follows. So I have to take a vector here, and you say that this is V applied to F compose phi. Sorry. So, Okay, so this, I will explain it again and write it again. So I have to take an element here. So this V is in here. And now this is a derivation on Rn. So I have to tell you how it acts on functions in Rn, on germs of function in Rn. And the way it acts is that you apply the derivation V, which is the derivation on TPM, to the function f compose phi. Actually, not to the function, but to the germ, because that's how we define a derivation at the point P. And this is for f phi P in Rn phi of P. And we observed that also this is a vector space isomorphism. And again, the idea here is to to consider phi inverse, and this is a diffeomorphism, so everything works just fine. So now, what were we doing all of this? Well, the idea is that we want to study this TPM. Yeah, we want to, okay, we know now it's a vector space, and oh, good thing. And we want to study it a bit. For instance, we want to find a basis for it. And this isomorphism is what is going to help us because we know how this thing works very well. So let's define a few some derivations at P. So define d in dxj at P of f as the derivative. So this is just a symbol in a way. This d in dxj at P is going to be a derivation of TPM. So maybe let me. Yeah, so it's a derivation TPM. So I have to tell you how it acts. Function TPM. And we take f composed phi inverse. And now this is a function from Rn to from an open subset of Rn to Rn. So we can really take the actual derivative. So this is really the derivative. Okay. So this is for f in infinity mp. Okay, so while this is just a symbol on the left, this is really the derivative. Let me actually write it down. Symbol, true, real derivative. This is the standard derivative. And the lemma here is that the set made of such derivation is a basis for TPM. Okay. Let's prove it. So we can assume simply that m equal Rn, because all of these are isomorphisms. Yeah? So this I'm defining it this way, but then I can simply think of this as the actual derivation on Rn when we fix a chart. And we can also assume that P is nothing but the zero vector, which the zero vector will always call it just zero, even if it's the zero vector technically. And now we take f, which is book function on Rn as zero, so not a function but a germ, sorry. And we take a derivation at this point. And then we just compute a bit. We say, okay, v of f, and we expand this in Taylor series. Up only to order 1. There you have a remainder, which is order 2. And the claim here, so let's say this is claim. Now to explain you why. is just the same linear combination, so Cj times V of xj. Because these xj, you can think them as coordinates, let's say, but you can also think them as functions in the sense that you take the n tuple x1 to xn, and to that you associate xj. So since they are functions, particularly germs of function, they define a germ of a function at 0, so we can apply a derivative to it. And okay, why is this true? There is 3 reasons which they should fit in here. Okay, the first reason is that V of a constant is equal to 0. And the proof of this fact is an exercise. So these kinds of derivations of this f of 0. F of 0 is a constant, so V of f of 0 is 0. We don't care about it. Then, no, blue. V of Cj xj is Cj times V of xj, and this is trivial, it's just linearity. It's this first condition here. And the third one, so basically we're basically done. The only thing we need to show is that V of a big O of x squared is also 0. And this is a bit harder exercise. But the hint is to use the last property. Sorry, didn't really fit enough. Yeah, the idea is that it's not exactly like this. You have to be a bit more careful, but think of this as like the product of two functions which are 0 in the point. Yeah. And so this would mean like it'd be a O as a big O of x. So big O of x squared, you can think of like two functions and both of them are 0. So when you apply something like this is still 0 and this is still 0. To be a bit more careful, but that's the basic idea. And so this gives us this finite formula, yeah, this claim. And in particular, this implies, oh, sorry, that V is the sum for j equal 1 to n of V of xj times d in dxj at 0. So I'm now retaking this notation that we had before. And why I'm saying that this is the case, well, because this is how it acts. Yeah, if you take V and you take V of f, then what you get here is Vxj times the derivative of f with respect of xj at 0. And this is exactly what happened here. Yeah, because these Cj's are the derivatives of so right here, because Cj from the previous slide is exactly the derivative of f with respect to xj at the point 0. Okay, this is because it's a Taylor expansion. So this formula clearly implies that these ones are generators. Generators as a vector space, simply because we took an arbitrary V, an arbitrary derivation. Where is it? Yeah, we took an arbitrary derivation and we expressed it as a linear combination of these factors here. To show that it's a basis, we need to show that they're also independent. So show they're independent. Okay. Vertical line. Okay, so now that we have this notion of differential from, but we only defined it really, this notion of differential, we only defined it for local charts for now. Yeah, we say, oh, this is what we call the differential, but we only really define the differential of a local chart. So let's try to be a bit more general. And we take M and N to be manifolds. And here it really doesn't matter if they're smooth or complex. So F and N, smooth map. Of course, now I'm doing everything for smooth, but again, this also works for complex. So we take a point, and now we define the differential of this map in a point P. So df at P, that's how we denote it. It's a map, linear map, from tangent space at M to tangent space of N, such that. So as usual, I have to, so we take a V in here, and this should be a derivation at Fp of N. So I need to apply to a germ of a function to tell you how it works. And as you might imagine, it's just this. And here is for V in TPM. H, it's a germ of a function on N at F of P. Okay. So it's really, we're really mimicking what we did here. It's really the same thing, but it's just a bit more general because of this. Okay, and now it's maybe harder exercise because it's really a proposition, I would say. But let's take a point in M, and let's take a function from M in N smooth. And let's take a chart, local chart around P. So what it means, local chart around P, it just means that P is in U. And we take another local chart for N this time around the arrival point. So VPC, local chart around F of P. And write phi of Q equal x1 xn. And C of Q prime equal y1 y. Actually, I'm going to use n here and m here for consistency. No, x m should have dimension m, and n should have dimension n. So we write it like this for Q in U and Q prime in V. Yeah, so this is, I'm basically just giving names to the coordinates in Rn, in Rm and Rn. Yeah, just to give it a name. Then prove that the matrix of the linear map df p tpm dfp n with respect to the basis d dx1 at p d dxn m at p. So this is a basis of TPM, we said. And now we also need to give a basis of TFPN, which you can imagine is just dy1 at f of p, dyn at f of p in tf of p n. is the Jacobian matrix, is the Jacobian matrix of nothing but C inverse composed F composed phi at the point 5p. Okay, so let's just recap what we're asking here. So you know you have your M, you have your N, this you have your F between them. Yeah. And here you have your U, and this is phi. Did I make a mistake? Yeah, this should be the opposite. Yeah, this should be phi inverse. Because this is phi inverse. This is psi v. So we know that all of, I mean, this F gives rise to df of p. So dpm, dpn. And basically what it's telling us, this proposition, this exercise, is that if we take the correct basis here, which corresponds, sorry, not p, but phi something point, what it's telling us is that this kind of diagram also works for the differential. Okay. And the fact that we choose the basis that really comes from this map, as we showed previously, and here we also choose the basis coming from this map specifically, gives us that when we take this differential, we get the correct one. Let's say the one we expect. Okay, I think this is enough about tangent space, structure sheaf, and maps between them, and also we define the differential. So now I'm going to recall the definition of some manifolds and some important theorems related to them. And we will skip all the proof. So we take M, smooth or complex, manifold of dimension n. Then we take a topological subspace, so topological subspace n contained in M is a regular submanifold of codimension K if for every point in the submanifold, this topological subspace for now, there exists a local chart U phi near P. Again, this near P, around P, center to P, just means that P is in U, such that if we intersect this n with U, so if we look at this n only locally, what we get is that this is precisely this hyperplane. Yeah, so what we're saying is that topological subspace is a regular submanifold if locally it's nothing but subspace, yeah, flat. I mean, it doesn't need to be flat. I mean, you understand that it's equivalent if I ask at the first k coordinate are 0, or if I have k independent function which are 0. So it's just a n minus k subspace, n minus k dimensional subspace.
Do we require to that n is closed?
We do not.
Okay.
So given, but is it? We do not require it, but does it imply it?
I don't think so, because if
Because you're thinking of immersive manifold, you're thinking of things like
yes,
this, yeah? So here, I mean, we know what this is.
and I think if we only require the existence of a local chart, it does not have to be.
But
For
normally,
example,
yeah.
the interval from -1 to 1 in R squared, so just the one-dimensional interval in R squared, should be a regular submanifold if we require it like this.
No. Oh yeah, sorry. Yeah, because I asked this be yeah, exactly. Yes, you're correct. Let me check with my notes if I yeah, you're perfectly correct. So the difference there, the thing I thought I defined it this way, I will I will check more properly later. But if you ask that this is true only for P in N, then you're correct. This open interval between 0 and 1 is a regular submanifold. But actually, if you ask the same thing, but for every P in M, yeah, the open interval between 0 and 1 in R2 is not a regular submanifold. Because if you take the point 1, 0, then you don't have such thing. But yeah, we don't require it to be close. So for me, 0, 1 in R2 is in fact a regular submanifold.
Okay.
Regular submanifold. Then for every P in N, there exists a neighborhood U of P and the smooth F from U in Rk such that n intersected U, the set of all Q in U, such that f of Q is equal to 0. What happened here? And the differential is surjective. Very Q now. Yeah, so this is kind of what I was saying before. That we do have some freedom. And if you look at this is like the local chart. So here's like if we were in our N. But what if we want to look at this directly from N? Yeah. So if we have a regular submanifold, how do we translate this local condition to something which, I mean, it's still local, of course, but it looks a bit more intrinsic. And the thing is like this, because you can just take f of q to be the projection on the first k coordinates of phi of q. Yeah, this satisfies all these properties. Because you see, when these are all zeros, then we're precisely in this unintersected U. Okay, and you get that the differential is surjective because when you move in this away, let's say when you move in the x1 direction, you get one dimension, and x2 direction, you get the second one, and then you get k of them. And since we're going into our k, you get k of them. So theorem, and this is probably the most important theorem here, which is the rank theorem on manifolds. So you know that whenever you start studying some manifolds and such things, one of the theorems that usually pops up, and it's very important, is the implicit function theorem or the inverse function theorems. In some sense, that you can all group this theorem into one big idea because they're kind of equivalent to each other. And I think this one that I'm going to state now is somewhat I mean, I cannot say it's the most general because they're all equivalent, but somehow it's the one that to me gives the bigger picture. So we take two smooth manifolds, M1 and M2, and the dimensions are n and m. Then we take a function f from M1 to M2, smooth. Assume that for every p in M1, the rank of the differential is k. So we didn't, let's say, properly define this, but this is the rank of a differential of a map. But you know the DFP, it's a linear map between two vector spaces, so you know what's the definition of rank there. Then for all points in M2, such that the inverse of A is not empty, we have that the F inverse of A, which is a subset of M, is a regular submanifold. Of codimension K. Sorry. Okay, thank you. I had some problem with electricity. And yeah, what I was saying before is that this is the most general, and general not really, because they're not equivalent, version of the implicit function theorem in a way. Yeah, because I mean, the idea is that here there is a lot of theorems in this flavor, which I believe you know and you studied them a lot already. So you have the implicit function theorem, the inverse function theorem, this rank theorem, and I believe this is the one that this expression here is the one that was going to be more useful to us in the future. And I think one good thing you could do if you don't remember this theorem as well is review this kind of theorems. Yeah, they're quite a lot, and I don't want to repeat each one of them. So this is just to give you the idea of what I'm interested in, of what I want you to know and remember. So this is more kind of a general exercise. If you don't remember them, then remember them. But otherwise, a more practical exercise to see if you have practice with these things. Let's just take a point in Cn plus 1 minus 0. And we take H to be a projective hyperplane. And you have to prove that H is a submanifold. Of CPM. Okay, so this is a more hands-on exercise. Again, it shouldn't be too hard. But it's good practice if you don't really remember these theorems. Okay, our review continues, and now we're gonna talk about covering spaces and group actions. So we start with two Hausdorff topological spaces. Topological spaces, and we assume they are connected and locally path connected. We take pi from x tilde to x, surjective and continuous. And we say that x tilde pi is a covering of x if for all x in x there exists a neighborhood, open neighborhood of x such that the anti-image of this open set is simply the disjoint union of open sets, and such that also we have that if you restrict phi to this utility of I, this is a homeomorphism. Homeomorphism for all I in this set of indices. Okay. And so I believe you told me yesterday that you've already seen this definition. And so let's just recall what maybe is the most important theorem here, which is the lifting theorem. So we take a covering. So if we have a path that is a map from 0, 1 into x continuous, which starts at some point in 0, then for all x in x tilde in the anti-image of x0, so for all points above x0, there exists a unique lifting. So that is another path such that it's a lifting in the sense that if you project it down, you get back your original thing, and such that it start at this x tilde. Okay, so you start with a path and you can pull it up, but you have to decide a starting point. So this is x tilde. There's only one way to pull it up once you decide the starting point. And this theorem also works for so-called homotopies. So if gamma 1 and gamma 2 are, again, paths in x, starting at the same point, and ending at the same point, and we have an homotopy between them. So that means that it's a map from 0, 1, closed, times 0, 1 in x. So this subscript here means that that's the name I give to the variable. Homotopy, such that f of 0t is gamma 1 of t. F of 1t is gamma 2 of t. And f of s0 is always x0, and f of s1 is x1. So I'm sure you've seen this already, but just to a reminder, basically you can think of f with respect, so the map that's an s to f of s comma dot is like a path in the space of paths, if it makes any sense. And what these conditions are telling you is that the image is always a path which starts at x0 and ends at x1, and that the first path is a gamma 1 and the last path is gamma 2. And then I made the mistake of not saving enough space for the conclusion. But then there exists a unique lifting. Now, of course, sorry, first I have to choose the lifting point like before. So we fix an x tilde in the anti-image of x0. And we also fix gamma 1 tilde and gamma 2 tilde liftings of gamma 1 and gamma 2 starting at x tilde, Then there exists a unique lifting f tilde from 0, 1 times 0, 1 into x tilde homotopy such that, okay, and of course it does what we want, which means that if you look at 0t, you get the lifting of gamma 1. If you look at 1t, you get the lifting of gamma 2. If you look at the starting point of each path, you get your x tilde, while the endpoint, well, this is going to be the endpoint of gamma 1 and also the endpoint of gamma 2. And this is in the anti-image of x1. Yeah, x1 was the endpoint of x1 was the endpoint of our two paths, and our lifting ends in something which is over this endpoint. And we have something more, which is even somewhat a farther generalization of these two things. So if W is connected and locally path connected topological space, and we fix a W0 and W, and a map phi from W to X, which is continuous and such that X0 is phi W0, then for all X tilde in this anti-image, there exists a unique lifting of this map. So lifting again means that pi composed phi tilde is phi. And phi tilde of W0, which was like our base point here, is x tilde. So this exists if and only if, so I'm not saying that this always exists, but it exists if and only if the induced map of fundamental groups satisfy this property. Okay, now I don't want to recall neither what is a fundamental group nor what is this induced map. I hope you remember this, but it is a property which is of course very important for coverings, and it tells you when can you lift maps into X to maps into X tilde. And it has this property here. And the reason I really want to do this is to define the so-called deck transformation group. Covering of X. Then this thing here, we define it to be the set of self-homeomorphisms such that pi composed F is just pi again. So we can think of them as symmetries of the covering, and this is the deck transformations group. And we can see that it is a group, in fact. Oh, that became red for some reason. It's okay. And a definition, covering of X is the universal covering if X tilde is simply connected. And again, I'll give you another exercise here if you don't remember this stuff. The map that goes from R to S1, and we think of S1 as the subset of C, that sends X to E to the IX, is the universal covering. S1. I mean, prove that. Yeah, exercises prove that this is the case. I'm saying the universal covering because you maybe remember from your previous courses in topology that the universal covering is unique up to homomorphism. So we talk about the universal covering. And also, so this is prove it. And since we're at it, you can also compute the deck transformation group. Yeah? And now I want to give one last proposition for which I will not give the proof, but for which I believe you've never seen the proof. So this is actually a proper exercise. And the thing is that, so all we discussed so far about coverings is all only for topological spaces. And this is usually the way people see coverings. So you see coverings in a course about topology. And you don't see them again, let's say. But if we take all this theory and we move it to manifolds, the proposition is that if you start with a smooth manifold, smooth or complex manifold, and you take a covering of this manifold, so a covering in principle is just a topological space, then the thing is that this covering can be given a unique smooth or complex structure that makes it a manifold. Yeah, so basically what this is telling us is that the covering of a smooth or complex manifold is itself a smooth or complex manifold. And there is basically one way to do this if you require this pi to be in the correct category, so smooth or holomorphic. So I think you've never seen this, so this is like more of a proper exercise. It's not a recap exercise. It's more like, okay, let's see if you understood the definition of manifold well, these kind of things. Okay, so to conclude the review overall and to conclude today, we will talk about Lie groups and group actions in general. So a group G is a Lie group if it is a smooth manifold such that the map that sends GH to G composed H inverse is smooth. We can also talk about complex groups, and then it's a complex manifold such that this map is holomorphic. And here we have examples, and it's basically all the linear Lie groups. So linear Lie group is a group of matrices. Linear stands for matrices. And if instead of instead of R you put C, then you get all the complex Lie groups. So that's basically all I'm going to say about Lie groups. That's the definition and examples. And let's talk now about actions. So we take a smooth manifold. And we define its group of automorphisms as the set of all maps from M to M, which are diffeomorphisms. So self-symmetries. And we say that the group G acts on M via phi G out M, so G acts on M, if phi is a group homomorphism. So basically what we have is that every element of G defines an automorphism. And the action is faithful. Or sometimes effective. So this is two different names for the same thing. If phi is injective. Yeah, so the only group element which fixes all the points is the identity of the group itself. And our first example here, we already saw it, is of course the Dirac transformation group of a covering. Yeah, so this is our first example, we already saw it. So here I'm not saying that G is a Lie group, it's just a group. And this is a group and it acts on our manifold. Acts on X tilde, of course. Okay. So what is the orbital point? So we start with an action, given an action. The orbit of a point x in M is G times X and is phi of G. So this is an automorphism and we apply to X. Yeah, so we're simply taking X, applying all possible elements group, and what we get is the orbit. And notation. We will never write this ugly thing because it's long and weird and boring. We'll simply write G dot X. Okay. And once we have a group acting on a manifold, we can define a relation such that X is equivalent to Y, if and only if they're in the same orbit. So but let's do it properly. So if there exists a G such that G X is Y, and this is equivalent to saying that Y is in the orbit of X, this is also equivalent just to say that the two orbits are the same. Okay, so I think these arrows are straightforward. If not, ask or verify it yourself. And then we have the quotient. M mod A is usually written as M mod G. Is the so-called quotient space for the action. Is the quotient space for the action. Sorry, this is the. Okay. And an interesting exercise, which I think you never did. I hope you never did. Is that M smooth manifold. And here it's really important it's a smooth manifold. This doesn't work for complex. Smooth manifold. Then M mod out M. And here the action is the obvious one. So you have an automorphism, you apply the automorphism is a point. So what I'm saying here is that the action is transitive. And I didn't define what transitive means, but well, you can say that it means exactly this. So there is only one orbit, and that orbit is the all of M. Okay, so I believe this concludes chapter 1, which is the review chapter, and it concludes today's lesson. So do you have any question before we close it? Okay, if not, I wish you a good weekend, and I will see you Thursday when we will start with something hopefully completely new to you.
Bye.
Okay, have a nice weekend.
Have a nice weekend. Bye.